In this video, I'll be going over chapter 1 and 2, which were the chapters tested on for exam 1. I'll also be doing uh, the questions I got for exam 1 while going over chapter 1 and 2, while going over these notes. And these notes and these questions will be put in the description under this video. So, intermolecular forces are forces of attraction between separate molecules. So, this is an intermolecular force, this is an intermolecular force. And these bonds aren't intermolecular forces. And they give physical properties like states of matter. Just to review what polar and nonpolar molecules are. Polar molecules are molecules with the positive and negative end. So they're lopsided that way. So CO is a polar molecule because there's a positive and a negative end. And H2O is also a polar molecule because there's a positive and a negative end. So it's lopsided and not balanced. Nonpolar molecules are balanced, so they don't have a positive or negative end. So for example, N2 is a nonpolar molecule and CO2 is a nonpolar molecule. And nonpolar molecules include homodiatomic molecules, which are just like these, N2, O2, Br2. And nonpolar molecules also include hydrocarbons, which are molecules that only contain hydrogen and carbon. And the three types of intermolecular forces are London dispersion, dipole-dipole, and hydrogen bonding. London dispersion are found in all molecules, so any polar and nonpolar molecule will have London dispersion force. And I put that there's a little tiny electronegative difference, electronegative in electronegativity difference for even for nonpolar molecules, because there's electrons around these elements, right? And as these electrons are constantly moving, and as they move, sometimes there's more electrons on one side and there's less on one side. So there's a tiny, there could be a n that's a little bit negative and the n that's a little bit positive. So, and we call this an instantaneous dipole. So all polar and nonpolar molecules can, or it meant that molecules with London dispersion force can develop a temporary instantaneous dipole. Now the next intermolecular force is dipole-dipole forces, which only happen between polar molecules. And these polar molecules have permanent dipoles. So there's a partial positive charge on one side and a partial negative charge on the other side. And stronger dipole-dipole forces means there's a larger electronegativity difference, which is a relationship you probably don't need to memorize and you can just make sense of, because dipole-dipole forces exist because there's a positive and a negative side. And if a more positive side and a more negative side exists, the dipole-dipole forces will also exist more. So hopefully that makes sense. And the third type of intermolecular force is hydrogen bond, which are which happen when hydrogen bonds with either fluorine, oxygen, or nitrogen. And hydrogen bonding is a type of dipole-dipole attraction that is especially strong. And actually, I don't think you need this. And I'll make this small. Now, and also, out of these three forces, hydrogen bonding is the strongest intermolecular force. Dipole-dipole force is the second strongest, and London dispersion is the weakest intermolecular force. And besides this relationship, there's also this relationship where, for example, intermolecular force is directly proportional to molar mass, directly proportional to melting and boiling point, inversely proportional to vapor pressure, directly proportional to viscosity and surface tension. And molar mass is also directly proportional to this, and inversely proportional to this. So, for example, for an example of how to use this, let's say in a question there's a there's something with the molar mass of 100 and there's something with the molar mass of 200. Then the one with the molar mass of 200 would have stronger intermolecular forces, and the one with 200 will have a higher melting and boiling point and have a lower vapor pressure. And let's say in another question, there's water and honey, for example. Honey has, of course, a higher viscosity because it flows slower. So honey also has a higher surface tension than water, and the intermolecular forces in honey is stronger than water. And just some definitions, you probably know this, but viscosity is the resistance to flow. So honey has a higher viscosity than water. And surface tension is the energy required to increase the surface area of a liquid, which is a kind of confusing definition, but it's the property required or property responsible for the beating up of a liquid. And now I'm gonna do some questions on the test, or that showed up on my test. Which of the following halogens would have weaker intermolecular forces? Br2, I2, CO2. You know how I wrote step 1 and step 2? Well, when you see, let's say, these three compounds, you don't you don't compare their molar mass first, for example. You determine which of the three types of intermolecular force it is. And we know Br2, I2, and CO2 are homodiatomic molecules, so they're all nonpolar, meaning they're only they only have London dispersion forces. So they do have the same type of intermolecular force. So now we need to try step 2, which is using these relationships. So we know, or we see that Br2 is right here, I2 is here, CO2 is right here. So CO2 has the lowest molar mass. So, and we know higher molar mass means stronger intermolecular force. So lower molar mass means weaker intermolecular force. So out of these three, CO2 has the weakest intermolecular force because it has the lowest molar mass. And next question, what's the predominant intermolecular force in NH3? Well, we know NH3 has N and H, and there's a bond between them. NH3 has hydrogen bond. Next question, out of these four, actually never mind. This question is for something else. Next question, also, also, for a solution to form, the solid and solvent must have similar intermolecular forces. So, for example, ethanol and water both have hydrogen bonding, so they mix. So out of these four, which are most likely to mix and form a solution would be what? Well, this is a this is a hydrocarbon, so it would be only London dispersion force. This is also a hydrocarbon, so it would be London dispersion force. So it might be this one. This, there's N and H, so it's hydrogen bonding. And this only has carbon and hydrogen, so it's a hydrocarbon, so it's a London dispersion. So this is a hydrogen bonding, and this is a London dispersion, so it's probably not this one. This one, NF3, is a polar molecule, so it's dipole-dipole, and SO2 is also a polar molecule because there's a there's a slightly more positive side and a slightly more negative side, so it's also dipole-dipole. So it might be this as well. CO is a nonpolar, and so CO is my CO is a polar, so CO is a dipole-dipole, and this is again a hydrocarbon, so it's London dispersion. So we know both of these are both of these are only London dispersion, and both of these are only dipole-dipole. Well, you know how we said similar intermolecular forces? Well, these two are both hydrocarbons. They only both have carbon and hydrogen. And this one, even though they're both dipole-dipole, they're very different elements. And when they form, they'll have di they have different shapes when they form. So these two are the most similar. And the most similar means they're most likely to form a solution. So this is the answer. And we also went over this. The property responsible for the beating up of water is surface tension. Next, next topic, it's just a formula, and you don't really have to understand what this formula's solving for or anything else about it. And Once you see this in a question, you'll know out of the whole equation sheet to use this equation. So you just need to know how to plug stuff in. So and something to be careful of is the units, and make sure temperature is in Kelvin. So I'm not gonna do this question or work it out with you, but what I would do is first convert this to joules per mole, because on the equation sheet for R, it's joules times uh, Kelvin times mole. Wait, joules over Kelvin times mole. So I'll convert this to joules per mole, which is like 39,900. And then this is temperature 1. I'll convert this to Kelvin by adding 273 to here, and then this is pressure. I'll put it here for P1. This is pressure 2, P2, and then after plugging all the values, solve for T2, which is in Kelvin, and then I convert that back to Celsius. Now the next topic, it's also pretty easy. It's just a chart of temperature and pressure. You don't have to understand this too much. Just know this area is gas, this area is solid, and this area is liquid. And this is a triple point because it comes in contact with all three states of matter. So all three states of matter exist at this point. And critical point is the point where liquid and gas phases become indistinguishable. And just remember that you probably know freezing, melting, vaporization, and condensation already. So just know that when a solid goes to gas, it's sublimation, and when a gas turns into solid, it's deposition. So we can answer these two questions with it. This is pretty self-explanatory. This would be solid, and when something from solid converts or changes to a gas, it's sublimation. Next topic, it's also a pretty short one. Ionic solids are a metal plus a nonmetal, or a polyatomic ion plus a polyatomic ion. Or it can be a mix, like a metal and a polyatomic ion. Metallic solids have a metal element, so it like copper and iron. Molecular solids only have non-metals, so like carbon dioxide and water. So out of these four, which of the following is considered an ionic solid? It would be this, because it is polyatomic ions. And I2 would be a molecular solid, because it only has nonmetals, and Cu, copper, will be a metallic solid. This is just a random question, not really tying to anything we've taught about so far. As a solid element melts, like melt into a liquid, the atoms become more separated because it melts and they have less attraction for one another because as they melt, they're farther apart, or the atoms are farther apart. Next topic, it's this. It's also a pretty easy topic. The solubility of a compound in a particular solvent is the maximum concentration in solution that can be achieved. That's just a definition that you hopefully already know about. Here's the important part. When the solution contains the maximum dissolved solute, so the concentration of the solute is equal to its solubility, this is called a saturated solution. When there's the concentration of a solute is less than its solubility, it's and there's more solute that can be dissolved in the solution, then this is called an unsaturated solution. And when there's more, or if there's a higher concentration of solute than its solubility, then this is called a supersaturated solution. And the solubility of a gas is highly dependent on both pressure and temperature. Now the next part is colligative properties. Sorry, I forgot to add here. In these type of questions using this formula, if it says for something at normal boiling point, then we use 1 atm for the pressure. So colligative properties depend solely on concentration. So it doesn't depend on other things like states of matter. And colligative properties include these type of equations. Vapor pressure of a solution equals the mole fraction of solvent multiplied with vapor pressure of the solvent. The temperature, the change in temperature of the solvent is equal to the I is a Van Hoff's factor, the I of solute times the temperature in K of solvent. No. K is in the temperature. K is the molar constant, but we'll get to that when we do a question. Times, so I times K times molality. And we'll get to more details about this when we actually do questions using these equations. I is called the Van Hoff factor, and for non-electrolytes like sugars and alcohols, they have an I of 1. For other stuff that aren't sugar and alcohols, which are called electrolytes, we need to count ions for the I. For example, NaCl dissociates into that and that, so they have IO2. This dissociates into that and that, so it has an IO2 as well. MgCO2 dissociates into that in two of these, so it has an I of 3, and this dissociates to this and three of these, so it has an I of 4. Now I'm gonna do some questions using what we just learned. Identify the solute with the lowest Van Hoff's factor. NaCl will have a Van Hoff factor of 2, so I would be 2 for this. FeCO3 will have a Van Hoff factor of 4, so I will be 4. Glucose, remember, uh, glucose is a non-electrolyte, so they have an I of 1. So this would have an I of 1, and this would have an I of 3. So glucose will be the answer for this. Next question is just the definition we went over. Wait, actually, no, or kind of is. Remember how we said over here, colligative properties depend solely on concentration? So this would be false, because boiling point is one of the colligative properties, one of the 4 colligative properties. So boiling point, a colligative property, doesn't depend on the identity of anything. It only depends on concentration. And osmotic pressure and freezing point is the other 2, or 2 of the other 2 out of the 4 other colligative properties. And I guess we can solve for this. So vapor pressure is the mole fraction of solvent times the vapor pressure of the solvent. And mole fraction of the solvent is also equal to the moles of solvent over the moles of the solvent plus the solid. So I wrote that down here. So the question is asking, is this true or not? When the solid is added to a liquid, meaning the solid is a solute, so if this increases, if this increases, this will increase, right? This whole thing will increase. And if this whole thing increases, this whole thing at the bottom increases, then this whole thing would uh increase. Like for example, if we go 1 over 3, it turns into 1 over 2, then that increases. And if this increases, then this also increases. So this would be false, because the vapor pressure increases when there's more solute, when there's solute added to the solvent. Next question is also on vapor pressure. Wait, yeah, it is. So we basically just plug everything in. The moles of solvent Well, solvent would be ethanol because there's more of it. I should probably add somewhere here. The solvent is what there's or the solvent is a substance there's more of. So in this question, the solvent would be ethanol, and it's already in moles. So it would be zero point 0.9 over the moles of solvent plus the moles of solute. And vapor pressure is 0.459 atm. And you just plug everything in to get 0.413, which is the answer. Next question is on freezing point. Freezing, the equation for freezing point is that the change in temperature of solvent is equal to IKM. Let me write that down. The temperature of the solvent is equal to the Van Hoff of the solute times the freezing point constant times the molality. So we know molality is 0.015. So this is 0.15. I is 2. And Kf of water, Kf of water is 1.86. And we just solve for that, which is equal to 0.0558. And the thing about boiling point and freezing point, the thing about this equation is there's two steps to it. So for boiling point, we add the boiling point temperature to the value we got. But for freezing point, we minus we minus this value we got, the change of T of solvent, minus that from the freezing point temperature. Now we didn't get a freezing point temperature for this question, but we know the freezing point of water is 0 degrees Celsius. I should probably add here to clarify, this is a freezing point temperature of the pure solvent. This is boiling point temperature of the pure solvent. So we do freezing point temperature of the pure solvent. The pure solvent is water because this is being dissolved in water. So the pure solvent is water, and the freezing point temperature of water is 0 degrees Celsius. We know that. So we do 0 minus that the change in T of solvent that we got, which is equal to that. So the answer is rounded is that. Next question. Of Out of these four, a zero point 0.1 aqueous solution of which one will have the highest freezing point? We should first see what the change in T of solvent is for each of these substances. We know change in T of solvent is equal to I plus Kf plus M. Okay, I wrote it over here. So the I for this would be 1, 2, 3, 4, because there's 3 of these. So the I of this is 4. The I of this is 1, 2, 3. So that the I of this is 2. And the I of this one is 1, 2, 3. Now the K is the K of the solvent, and the solvent is water, and the K for water is the same. So this this K will be the same for all of this. And we don't know molality, we only know molarity. But if you look at the equation sheet, molarity is that. And the molarity for each one will be the same. We're trying to find the molarity when there's the same molarity for each one. And if the molarity is the same, the moles of solid and the volume of solution is probably the same. And if the moles of solid is the same, and we don't know the mass of solvent, but solvent's water, and if we were using, if the volume of the solution's the same for each one, then the mass, the volume of the water used is probably the same as well. So the mass of solvent is probably the same. So if that's the same, that's the same. Molality is probably the same for each of these as well. So we know off of this, this has the largest changeability of solvent. And this, oh my god. And this one has the smallest changeability of solvent. So, and these one are like in the middle. And the question asks, what has the highest freezing point? Well, freezing point is freezing point minus the changeability of solvent. Well, if the freezing point is minused by the largest change of solvent, then it would be a small number. Let's say, for example, the freezing point, or let's say that we don't know this, but let's say the calculated was 5. And let's say the calculated change of solvent from this is 3, just as an example. And let's say freezing point temperature of the pure solvent is 10, right? If we minus this from the largest number versus if we minus it from the smallest number, or the smallest change of solvent, then the freezing point temperature that's minused from the smallest change of solvent will have the largest freezing point. So highest freezing point. So NaCl would be our answer. I hope that makes sense. And this question, put them in order of increasing osmotic pressure. Well, osmotic pressure is, the formula for it is I times M times I times molarity times the R value times temperature. And the I for sucrose is 1 because it's an it's a sugar, so it has an I of 1. The I of glucose is also 1, and the I of glycerin is also 1 because it's an alcohol. So the I for all of them is the same. The R is just a value, the R value. It's a constant, so it's also the same. Or it would be the same if we calculated osmotic pressure. Or we would use the same, we would use the same R value when we calculate osmotic pressure. And temperature, it doesn't tell us that it's different, but we can assume it's the same. The only thing different is the molarity. And if there's a higher molarity, there's a higher osmotic pressure. Just from looking at the formula. So sucrose would have the highest osmotic pressure, followed by glycerin and glucose. So it's 1, 3, 2. Wait, increasing. So it's 2, 3, 1. So it's, yeah. And then same thing here. There's already an answer, but that has an I value of 1. That has an I value of 3. That has an I value of 2. And it's like the same thing here, except now molarity is the same. Molarity is the same, R is the same, temperature is the same. So the one with the higher I value will have a higher osmotic pressure. So the answer would be or this would have the highest osmotic pressure, followed by this and this. So that's the answer. And let's say there's a question that shows up where there's a different molarity and a different I value. Well, you would just plug it in and then solve for it. Last two questions. I didn't go over it in the the video, but we can figure it out just by looking at the equation sheet. So this question, the concentration, so we're trying to find molality because by looking at the units, we know we're trying to find molality. And molality is the moles of solute molality is the moles of solute over the mass of solvent in kg. We know the mass of the sol we know the mass of the solvent, but it's in grams. So we can convert this. 39 grams is 3,900. Wait. Yeah. 39,000. Wait, my bad. 39 grams is 0.039 kilograms. And we're trying to find the moles of solute. And we have the molar mass of the concentration of urea and the grams of it. So we can just convert that 16 grams of urea times we can just flip this because it's equal to 1. And this is equal to 0.267. Divide that and the answer is 6.8. Last question. Same thing where we just use one of the equations from the equation sheet. Mole fraction is the moles of A divided by the sum of moles. So the moles of A, well, we're trying to find sucrose, the mole fraction of sucrose. So we try to use the moles of sucrose, and we know the grams for it, 38.6, and we don't know the molar mass for it, but you hopefully know how to find it. The molar mass of sucrose is 342. Calculate that, and then you do the same thing for water, converting it to converting it to moles using molar mass, like that. And mole fraction is moles of sucrose over the sum of moles. So it's just moles of sucrose over the sum of moles, which is moles of sucrose plus the moles of water, and then calculate that and find that the answers that. That's it for this video. And a few more things. There's more questions under here, but it's pretty self-explanatory, so I'm not gonna go over them. Under the notes, there's more notes here, but they were notes that were covered in class that he even wrote down, but it wasn't covered in lecture. So, I mean, it wasn't covered in the exam itself. So, if you're reviewing for the final, I wouldn't worry about anything under here. And now that we learned everything, it's chapter 1 and chapter 2 is honestly pretty short. These you hopefully can understand already. Uh, this equation, you don't really need to understand it. You just need to somewhat know how to use it. This is pretty easy to memorize. This too. So like everything outside of these boxes, you should be able to know already. You should be able to memorize them just by understanding it. And there's only really three main things about chapter 1 and chapter 2, or three main things about exam 1. Is this, the solubility stuff, and the colligative property stuff. And before the exam, you hopefully memorize this as well, and hopefully memorize this as well. And before the exam starts, for on your scratch sheet of paper, I will write these three equations here, because they're harder to memorize. Wait, actually just these two equations, because this is going to be on your equation sheet here. Osmotic pressure is equal to I times m plus I times m times r plus times t. So it's just these two equations that you can't really use the equation sheet for, because they're written shortly and they don't tell you if you should use the mole fraction of the solvent or solution, that kind of stuff. So just try to write this on your scratch sheet of paper before the exam starts.